now turn over to Professor Schenck from Oberth, who's going to tell us great stuff, I'm sure.
Thank you. So I'm going to share screen for 1 second, then I'm going to go. So this is actually going to be an old school talk. So when our university, can everybody hear me? I should say first.
Yes, perfect.
Okay. So let me share screen real quick here first. So this is the motivation for the talk is here. So there's two types of symmetry. So the first type of symmetry at the top is coming from a Gorenstein ring, and that's something called the Betti table, which will be the second part of my talk. And of course, the second diagram is the Hodge diamond of Clavial threefold. So I'm going to stop sharing there, and then we're going to go to the blackboard. Yang, can you mirror this?
How would you like me to?
Just a regular Zoom. If I have the Zoom window, I've got the black. This is an honest to God chalk talk. So just if I'm up on the.
Let's see. How do I do? I mean, just to.
I think all viewers, if you double tap on Hal's screen, you can pin it, and it will make his the centerfold screen of the.
Oh, I see. Okay, so
there we go. All right, perfect. So let's see. So. All right. So this seems a bit odd, but when we went to all remote instruction, I took over calculus for the whole university. And we tried various different mediums and of the iPad and the slides. The students like the old school Blackboard talk the best. So we are going to have a Blackboard talk here. So I've cheated a little bit by preparing my Blackboard. The title of the talk is Symmetry from Physics of Clavials to the Algebra of Gorenstein Rings. And you guys should all feel free to unmute and shout questions at any time. I'm going to actually cheat. So it's really not going to be the physics of Clavials. It's going to really be the geometry. And so this is joint work with Mike Stillman and Beiwei Yuan, both at Cornell. The Beiwei's moving to Swansea. It's on the archive. I'm just going to say a few brief words at the outset about the physics. So this is motivated by work that started in the mid-'80s and went through the '90s of Candelas and collaborators, including Horowitz, Strominger, Witten, Linker, Shimrick, De La Asa, Green, Parks. So these are the physics papers that sort of brought Clavials into the forefront. And then the jumping off point really is a paper of Green, Hübsch, I think I saw Tristan in the audience, and Lütken from about 1990, where they classified sissies. So sissy stands for CICY, that's a complete intersection Clavial. So these are Clavials that are complete intersections in products of projective spaces. And then the references sort of for the second part of the talk on the algebraic aspects, Gorenstein rings, starts about 20 years ago with a paper of Rodland, and then continues with work of Bertin, Coughlin, Bobiowski, the Kapushkas, work of Brown, Georgiadis, and Brown, Kasperzik, and Zhu. So I want to make sure I got the names on the board so that folks feel they're getting credit. I'm certainly missed a lot of people. And so now on to the sort of outline for the talk. So the where we're going is two parts. So for the first half of the talk, we'll be doing geometry. And in the interests of symmetry, in fact, mirror symmetry. So the second talk was Andrew Dancer, and Andrew started with the dot product. And I thought, good luck with that. Let's see how far you get. And so, of course, it's very tempting as the next to last talk to assume that everybody is now an expert in Clavials. But instead, I decided I would double down on Andrew's talk. And in fact, to go back earlier than the dot product. So we're going to start in 8th grade. So I'm going to start off with manifolds, the tangent bundle, exterior powers, and the canonical sheaf. Then we'll talk about Clavials, Hodge theory, the Hodge diamond, and various constructions of Clavials. So this is, of course, either going to be old hat for the experts in the audience, or it will be drinking from a fire hydrant from the neophytes. But then we will switch from there and do some algebra. So then we'll talk about free resolutions, Betti tables, complete intersections will again appear. And then Giancarlo Rota in How to Give a Talk says that every talk should have something for the audience to take home. So for the last 10 minutes of the talk, this is the take home here. So I'm hoping that this, in fact, having looked at the audience, I think that this is sort of terra incognita for many folks. So Gorenstein rings. There's a beautiful and elementary construction of Gorenstein rings. And this is all relevant to this sort of piece of the puzzle. Gorenstein rings generalize complete intersections. So, and this construction of Macaulay dates to 1916. It's super concrete and super computable. And in the end, we'll go back to that picture that I shared at the beginning with the two symmetric objects, the Hodge diamond and the Betti table. So that's it, game on. And let me, while I'm erasing, take any questions so far. Ordinarily, I would, if we were in person, Yang has been talking about beer and the joys of, say, being at Oberwolfach with an open bar. There's also, of course, the open espresso bar. And so I would be offering folks espresso prizes to participate. But we're going to dispense with that. So this is 1A, manifolds, tangent bundle, exterior power, and Kx. So back in 8th grade, so I'm now challenging Andrew here, we learned that the circle is a nice smooth object. And if we take a point on the circle, for example, P equals 1, 0, this is our circle C, we could draw a tangent line. So this is TP, the circle. Similarly, if we did the sphere, we might take the analogous point 1, 0, 0 and draw the tangent plane. So here's our sphere. And of course, there's not just one of these. We can see that at any point on the circle, we have a tangent line. At any point on the sphere, we have a tangent plane. And so we have, of course, a whole bundle of tangent x is now going to be some object. And the tangent bundle, T sub x, will have dimension. It's just a vector space. So a vector space is something like a line or a plane or 3 space. So the tangent space is going to be of dimension equal to dimension of x, and it will be a vector space. All right, so that takes care of manifolds in the tangent bundle. So let's see how fast we can do, the first month of the Carmo or something like that. So now I want to talk about the exterior product. So if one has a vector space, let's say 2-dimensional vector space with basis E1, E2, think of a basis as a frame of reference if it's foreign to you, or E1, E2, E3 perhaps. So this would be a 2-dimensional vector space, just R2. This would be a 3-dimensional vector space, R3. Then we can form ancillary objects. So the ancillary objects wedge I of V have, as a frame of reference, all tuples, EJ1 wedge up through EJI. This is for wedge I, with J1 less than or equal to less than J2, and so on. So in our particular, for say R3, we would have the basis E1, E2, E1, E2, E3. Wedge 2, we have E1 wedge E2, E1 wedge E3, E2 wedge E3, and then wedge 3. Just have E1 wedge E2 wedge E3. So again, this is a lightning tour of things. The point is that why would we care about these ancillary spaces? And the point is that one thinks of these in calculus as 1 forms, 2 forms, 3 forms. Those are things that one wants to integrate to measure volume. So in particular here, E1 wedge E2 measures the size of the determinant of the 2 vectors, and that's a little a little piece of area. In dimension 3, we would of course have a picture like this with a little E1 wedge E2, E3, which is a volume form. So we're going to want to, these exterior objects powers measure volume. And now let's flash back. Of course, the tangent bundle Tx was a vector space, V. And so we can form the exterior powers wedge I of Tx. And we're actually going to do this with linear functionals, so functions on that vector space. And this has a name. This is going to be called omega I of x, the I forms. And so this is the object that's going to be of interest to us in defining Clavial manifolds. There's a special case here, which we've already seen here, which is if I take the dimension of the tangent space and I raise it to, and I take that exterior power, I get something that has a basis of 1 element. And so there's a special name for if x is dimension n, then wedge n at Tx star, or let's just call it omega 1x, is called the canonical sheaf or the canonical bundle. So this is a rank 1 bundle. And so now we're ready to actually define. So that's our dramatis persona. So that's taken care of. And now we're ready to define part 2 of geometry, which is Clavial's Hodge theory and constructions. So again, this is a lightning tour. 1B. C-wise, Hodge, diamond, and constructions. So I'm going to have 2 definitions during this talk. The first definition will appear now. It's in the geometry section, and then we'll have a definition in the section on Gorenstein rings. So our definition is that HPQ is the dimension of HQ of omega P of X. So this is a vector space. These are things called cohomology groups. They are also vector spaces, and this has a dimension. And then, so these are the Hodge numbers. And then the definition of a Clavial manifold. So X is Clavial. So I think the first of the talks that this actually appeared in, so we've seen this, so I'm cheating a little, but this was in Xenia's talks. Xenia actually carefully defined Clavial. So X is Clavial if KX, the canonical sheaf, is just trivial. That is, it looks like functions on the manifold, and HI of OX is 0 for 0 less than I less than the dimension. So that's our definition of Clavial's and Hodge numbers. I've neglected to mention one key fact about the Hodge numbers, which is that they have a beautiful symmetry. So it turns out that HPQ is the same as HQP. So we're going to plot these numbers as a grid. There's 2 parameters here. So, and HPQ is HN minus P, N minus Q. So the Hodge numbers have a symmetry. Combined with these vanishing conditions, this says for right here, for a CY threefold, we can plot the Hodge numbers as follows. So 1, so we have this beautiful Hodge diamond for a Clavial, and in particular, there's only 2 interesting parameters. The 2 interesting parameters are this dimension H11 and H12. And again, the Hodge diamond has this symmetry. We fold it, and we can fold it, and we completely determine everything. This condition here is exactly what's saying we have the 1s and the 0s along these edges. So here is the question. So if Clavial threefolds, as was shown by the work of the physicists that we had on the board earlier in the 80s and 90s, are important for physics, then how do we find these? How do we find them? So this is great. This is like an Easter egg hunt, right? So we want to find Clavial threefolds, and we want to identify Clavial threefolds with various Hodge diamonds. And the mirror symmetry says that if you have such a X Clavial threefold with one thing, it has a mirror where the H11 and the H12s are switched. So you also want to find not just Clavials, but you're interested in what the mirror pairing is. So, so that's where I want to go next, is to constructions of such objects. And before I do that, I want to share the screen one more time. We've seen the beautiful manta ray figure. So my wife's a veterinarian. She always does these, when veterinarians give talks, they have these little images of animals and stuff like that. So I actually found an image of a manta ray with a diver close to a giant, one of the giant manta rays with a diver looking at it. I thought it would be a nice image for us, but I managed to restrain myself. So let's share screen here. And I want to do what? I'm going to share 2 other images. So I'll share this one first. Maybe I just share the whole desktop, that's easiest. And here is our standard manta ray shape of Clavial. So this is a plot of, it's not the H11 versus the H12, it's the sum of the H11 plus H12 on one axis and the Euler characteristic along the other axis. So this is a beautiful image. Where did I crib this from? Any audience participation for perhaps a prize the next time we cross paths at Oberwolfach or Oxford or wherever? Yang, you're not going to claim copyright infringement?
I think I'm not allowed to say. This looks just familiar.
So this is the distribution, which we've, and so these are all these plots are Clavials with various things. I want to now pull up an image from about 20 years ago, similar map. This was in Journal of Algebraic Geometry. Fabio Tonoli published a paper, and I want to draw your attention in particular to these 6 numbers that are sort of right on the periphery. In fact, they're past the periphery of the diagram. So these are Gokis, or projections of Gokis in P6 or P7. I can't remember what, but in particular, there's this 13 and 14, and you can see between the 13 and 14, there's actually an empty area here. And so if you go through all the tables of known Hodge numbers for Gokis, the first slide that I had up there with a 52 for the H12, that is a new one. And in fact, that lies right in the middle of those two numbers, 13 and 14. It's on the line. It's actually on the line right in the middle of that line, joining them. So I'll go back and stop the share and talk about constructions now. So I want to say something about constructions. So the first example that everyone sees is a quintic hypersurface 4, and one can then continue and look for complete intersections in Pn, of which there are 5. So there's 5 complete intersections in Pn. I'm trying to define every single term. So the idea of a complete intersection is if one has n equations, intuitively, each equation imposes conditions on your geometric object for the points to satisfy that equation. And so a complete intersection is one where one has n equations, and each equation actually does in fact cut the dimension down. So that means that the geometric object, the 0 locus of the corresponding variety, is codimension n. So that's a complete intersection. Things intersect transversely. So there's 5 of those. And then this paper that I mentioned of Green, Hooch, and Lutken from 1990 or 1991 classified Syzygy, complete intersection clavials, where they're in a product of projective spaces. So this is a beautiful paper. This is now suddenly you start to have a pretty good sized data set, a good size bestiary, right? A good sized bestiary of examples. And of course, if you're a geometer, when you look at a product, well, projective space or a product of projective space, that's the first and maybe second avatar of toric varieties. So then the next, I think, probably the most beautiful construction to me, BATY, is Victor Badyrev's construction of CYs in a toric variety corresponding to a polytope. So I want to say just a tiny bit about this. It's appeared in other talks so far, but again, it's worthwhile mentioning it. So one can build a geometric object called a toric variety from a polytope. So this is a beautiful, concrete, discrete geometric object. Polytope, you just take a set of points in some space. This is actually going to be points that are rational points. And then you take saran wrap and you pull the saran wrap around your point configuration, pull it tight, and what you get is a polytope. So of course, a polytope in 2 dimension is just a polygon. A polytope in 3 dimension is something like an octahedron or a cube. And so let me explain just a bit about this construction because it's so beautiful. So let's take, and this polytope is special, this is something called a reflexive polytope, and that means that there's exactly one interior lattice. So for example, a picture would be something like this. So here's an example of a reflexive polytope in 2 space. This is the origin, this is the point 1, 0, 0, 1, and so on. So this is exactly an example of such a thing. So now I want to talk about something that seems a little off topic, but it's worth mentioning because again, it's so beautiful. So somehow the aesthetics force you to say something. So I'm going to take my lattice polytope and I'm going to stick it in a 1 higher dimensional space in a plane, say z = 1. So pictorially here, I'm going to put this lattice polytope right here. And now what we do is we cone over the origin. So I'm going to form the cone, right? This is a plane sitting up here. I cone over the origin. And when I do that, I have another plane sitting down here at z equals -1. And when I do that, the normal vector to this facet is going to intersect the downstairs object, say similarly here. I have a normal vector here and two other normal vectors. And when you do that, you get what's called the polar dual polytope. Again, I just am taking the normal vectors to these, intersecting with the plane z equals -1. And we see that we get an object which is the polar dual, which looks like this. And Deus ex machina, right? This is, it's again, a reflexive polytope. So it turns out that if one takes a hypersurface, or more generally, one can use complete intersections, but hypersurface in a x sub p, this actually corresponds to a Clavial. And so it's even better than that, because this construction of the mirror pair, I mean, this is like, you know, it's almost like tout est pour le mieux dans le milieu de monde possible, right? We live in Candide's world. This is like the best of all possible worlds. So if you wanted a mirror pair, this is a mirror construction, right? And if you were lucky, if there was a God or something, then the mirror to the corresponding Clavial would be the mirror over here. And that's Badarev's construction. So this is beautiful. And so then I want to go one step further or beyond this. So notice here we're working with Clavials and various toric varieties. But now what complete intersections, my fault. So now what I want to do is I want to sort of change the game around and say complete intersections are a special case of a certain class of rings, which also yield Clavials. And so what I now want to talk about is something that I will call Gokis. So sort of in homage to the Syzygy construction, this is Gorenstein Clavials. And I had a list of names on the right-hand side of the board at the start of the talk. So Gokis also provide a stable of Clavials, and that's what I want to do next. So we're now ready to switch gears to the second part of the talk. I think I'm actually a little ahead of time. I know that Yang will not hesitate to gong me. I haven't been harassed too much yet, which is bad. I usually like to pause for questions. So any questions at this point? That was going from 0 to 60 in 17 minutes. So maybe the quickest introduction to Hodge theory and Clavials on record. All right, so now I have a pop quiz for the Monty Python fans, if there are any in the audience. So for the Monty Python fans in the audience, if John Cleese uttered a phrase which started these letters, so a six word phrase with that, what would he be saying? I promise
something completely different.
There we go. I was going to offer a beer. You cheated. Yeah. And now for something completely.
I didn't cheat. No, I just.
and now for something completely different. I can't do a very good British accent. So okay. So Gorenstein rings. So this is part 2, Gorenstein rings. And the first part I want to talk about. I'm not going to get to Gorenstein rings for a bit. I want to talk about free resolutions, Betty tables, and complete intersections. All right, so this is beautiful. This is my playground because this is, in a sense, very concrete and lowbrow. All it is linear algebra with polynomials. So let's take x squared, y squared, z squared. This defines an ideal in the polynomial ring. Let's just use K as our field. It doesn't really matter of x, y, z. So anytime I have a set of polynomials, I have an associated, let's call this I an ideal. I have an associated x equals v, an associated variety. In this case, this variety sits either in affine space or a projective space. Of course, it doesn't sit in projective space because we can see that the common zeros of this are where every variable vanishes, so it doesn't define a projective variety. And in affine 3 space, it simply defines the origin, but with some fatness, right? But with some fatness. So the question is, if we were given a more complicated set of polynomials, instead of something as nice as this. So, F1 up through FK and 20 or 30 or 40 variables. How do we understand the geometry of X? So how do we understand the geometry of X? And so the answer, or one answer, how to understand, so goal, let's say, goal is to understand the geometry. So we have the algebraic object, we want to analyze the geometry. And so one tool to do this is free resolution. So what we're going to do, let's call our ring S for the symmetric algebra. So what we're going to do is we're going to take S mod I, which is the coordinate ring of a variety in general. And now I'm going to start doing linear algebra with polynomials. And I'm going to use this as our example. This is going to be a running example. So we think of the generators of our ideal as a matrix. So I have a 3x1 matrix, and I want to compute its kernel. Now, this example has been chosen to be particularly simple because we can see each polynomial only involves one variable. And so the relations among these, which are called the Kazul syzygies, so there's our Scrabble word. A syzygy is a relation amongst polynomials. We can easily write down the obvious things. And that's all there is. And so we have a map from there to there. And we can keep going. The kernel of this is visibly simply z squared minus y squared and x squared. And the process stops. And so it stops by a theorem of Hilbert's from 1890 called the Hilbert-Syzygy theorem. So this is, of course, this is a toy example, but it illustrates almost everything that's going on. There's only one last piece of data that I need here to explain the top picture on my first slide. The top picture on my first slide had the first image that I shared had some sort of a symmetric grid of numbers. And so what we want to do is we're going to be working with projective varieties. So this is going to be, in general, I'm going to be interested in a homogeneous ideal, which is going to correspond to a variety X inside a projective space. And so homogeneous ideals are graded. And so what I want to do is I also want to encode the degrees of this map. And it seems a bit counterintuitive if you haven't seen it before. These are all quadrics. And so what I want to do is the image of this map lands in degree 2 over here. So I want the source of this map to also have degree 2 so that I'm preserving each graded piece. And to do that, we decorate this with a -2. This means the generators of this free module, this is just 3 copies of the polynomial ring. So this is a free module of rank 3. The generators appear in degree 2. And so that preserves the grading here. And similarly, the same thing has to happen here, except this has degree 2. I'm bumping up by quadrics. And so this has to have a 4. And similarly for the last one, again, I would offer a prize, but alas, we were not in person, it's a 6. All right, so this is called a free resolution. It's a bunch of free modules. So somehow the idea is that all the complexity of the ideal has now been encoded in these matrices that are our maps. And you might say, well, this information is essentially the same as the information over here, but this is going to, in a sense, provide, if we have the ideal, this will provide us lots of interesting geometric information about our objects. And so what I want to now do is I want to encode just the numerics of this. Just the numerics of this free resolution. I'm not worried right now, I'm not worrying about the maps in a little table, in a little grid. Might seem similar. We've seen grids before, right? So the grid that we're going to draw is going to encode first off the ranks of the free modules. So rank 1, 3, 3, 1. So that's going to go across the top of my diagram. Straightforward. This appears, the generator over here is in degree 0. So I'm going to start with a little picture here. This is degree 0. I have a rank 1 module in degree 0. That's straightforward so far. There's going to be one little piece. This is the only piece, so you should pay attention if you haven't seen this before. What I want to do is count over and down to encode this shift, because this is at step 1. And so what I'm going to do is at step 1 of the resolution, where does this 3 go is the question. And so I'm here in this column, right? This corresponds to this column, this corresponds to this column, this corresponds to the last column. And I want to count over and down. So I started, this is degree 0, 1, 2. So I'm going to put a 3 here because these are 2, 0, 1, 2. Same thing here. Now this is this is degree 4. I start here, I count 0, 1, 2, 3, 4. It appears here. And finally, the last one, 6, I've done 0, 1, 2, 3, 4, 5, 6. And so this is the grid. There's a reason for this. And the reason is that a fundamental invariant of any a sheaf on projective space is called the Castelnuovo-Mumford regularity. And that's exactly encoded in this diagram as the label on the last row. Now, what's happening, this is in fact a complete intersection, right? This is codimension 3. We had 3 polynomials. It's codimension 3. So this is a complete intersection. And we see this nice symmetric Betti table. And any complete intersection will have exactly this kind of a symmetric shape. Of course, if your generators are different, you'll have some spread out in the diagram, but it will be symmetric. And so there's a symmetry in the Betti table for a complete intersection. And now we're ready for the last part of the talk, which is Gorenstein rings. So Yang, I think I looked at my time. I think I have like 7 or 8 minutes left. Is that correct? All right. You're muted. How much time? How much? How many? You're still muted.
Sorry. Yes, 7 or 8 minutes is fine.
Okay, perfect. Okay, so this is the take home now. So Gorenstein rings. This is 2B. Gorenstein rings and Macaulay construction. So here's my second definition. S mod I, this is going to be polynomial ring. Homogeneous ideal. Is Gorenstein if, let's say, of codimension, I'm going to actually give my ideal a codimension of codimension C, is Gorenstein if X C S mod I S is isomorphic to S mod I A. This is some shift. So just like we had shifts in the Betti table, this is a shift or a twist. If you think about X's, if you want, you can think of X is equal to V of I, and then this is just OX of some A. So translating from commutative algebra to algebraic geometry. This may leave you cold if you don't like X modules, or maybe you love homological algebra and it doesn't leave you cold. So the point is really what this says is that the resolution, assuming that we're codimension C and something called Cohen-Macaulay, this says essentially that the resolution SOLUTI. So it turns out that if we want I to define a Clavial threefold, so if we want I to be I is equal to IX for X CY3, then this shift has to be, so the shift there has to be a -4 if this is a Clavial threefold. So, so what, you say? So example. So we've already talked about complete intersection. So this is the first example of a Clavial threefold that's Gorenstein, but not a complete intersection, which was due to Rodland. And more generally, it turns out that I should say Gorenstein codimension 3 is completely classified by a theorem of Buchsbaum Eisenbud. And it turns out that any Gorenstein ring of codimension 3 comes from the Pfaffians of a skew symmetric matrix of odd size. So the point, of course, is that if we have an odd matrix, which is skew symmetric, the determinant is going to be 0, because you're going to have the determinant is equal to minus the determinant. So you look at the submaximal minors. So if n is the size of our matrix, we look at the n-1 by n-1 minors. Those all have square roots. The square roots are called the Pfaffians. So if we did this, for example, for a 5 by 5 matrix of linear form. So let's say that this is 5 by 5 skew with linear forms. Then the submaximal minors will be 4 by 4. So we'll get quartics. And then we take the square roots of the quartics. So those are quadrics. And it turns out we have 5 such things. And the Betti table will look like this: 1, 5, 5, 1. So this is, for many of us, this would be the Betti table for an elliptic curve embedded by a line bundle of degree 5. Of course, that's a Clavial of dimension 1. Rodlin did this for, we want regularity 4. So Rodlin did it instead of a 5 by 5, he did it for a 7 by 7. And when you take a 7 by 7 matrix, of course, the submaximal minors are degree 6, and you take their square roots, and those are cubics. So you have 7 cubics, 7 linear relations on the cubics, and then a picture like this. So this is the Betti table for this first example of a Gorenstein codimension 3 Clavial, which is not a complete intersection. So that's our definition of Gorenstein rings. And in fact, the point is, for Gorenstein codimension 3, we completely understand the algebra. So then the sort of interesting question, which was essentially all the authors that I had over here on the right side of the board, is why don't we look at Gorenstein in codimension 4, where there is a nascent structure theory, but there is not a good structure theory. And so if we want a threefold, this is going to be, we're looking at some X, a threefold in P7. So this is what we're interested in, X3 and P7. Or X3 and P8 or P9 or higher codimensions, but this is our starting place. So how do we get such things? And that's really the punchline of the talk. So now is where, this is the something to take home. So the something to take home is, how do you construct Gorenstein rings? And it's a beautiful construction, and it's great because you can tell it to an undergrad. So this is Macaulay's construction from 1916. F is a homogeneous polynomial of degree, say degree D, contained in S equals K or X0. We let T be the ring of differential operators. And we look at F perp is the set of operators, let's say G in T, such that G of F is 0, right? I can take a polynomial partial differential operator, apply it to my polynomial, see which one's annihilated. So example, let's take F equals X, Y, Z for the Canadians. So what annihilates this? Well, visibly, if I take a linear form, it's not going to annihilate it, but some of the quadrics will annihilate it. And clearly, if I take x squared, here I'm thinking of this as an operator, d dx squared, that annihilates it because I only have one x. Y squared annihilates it, and so does z squared. And that turns out to be it. So this is equal to F perp. And we already saw this is a complete intersection. So this is an example of a Gorenstein ideal. The beautiful theorem. So what's the theorem? So here's Macaulay's theorem. Any Artin Gorenstein ring arises in this fashion. So Artinian means the ring has finite length, that is, as a vector space, it's finite dimensional. And you might say, well, I'm interested in Clavial threefolds. The coordinate ring is about as far from being a finite dimensional object as one could imagine. The point is that how do we study complicated geometric objects? Well, a natural way is to try to reduce the dimension by slicing with hypersurfaces, or best hypersurface of all, hyperplanes. So if we slice with hyperplanes, it turns out that for Cohen-Macaulay rings, of which Gorenstein rings are a type, you can slice them with hyperplanes until you're down to a zero-dimensional object and preserve, in some sense, all the crucial homological information. And so the idea here then is the following. So if any Artin-Gorenstein ring arises this way, and we have an arbitrary Artin-Gorenstein ring, so if S mod IX is the Gorenstein ring of a Clavial, we take the Artinian reduction, and we should be able to tease properties of this from the Artinian reduction. Better yet, we can see when we look at the Betty tables of all the Artinian reductions, the Betty table of an honest-to-God Clavial has to appear among that set of Betty tables of the Artinian reduction. So we have a way to filter the possible Betty diagrams for Gokis. And in fact, if you do this for the example I mentioned, if we do this for X contained in P7, when we look at the Artinian reduction, we find that there's only 16 possible Betty tables. And of those, we prove that only 8 occur for smooth threefolds. All right, and in fact, it turns out that all of these had already appeared in a paper of Coughlin, Gobolewski, Kapushkin, the two Kapushkas. But now that was P7. We don't have to restrict ourselves to P7. What happens if we go to P8? So when we go to P8, it turns out that instead of 16 Betty tables, there's 68 Betty tables possible for Artinian reductions. Many of them won't occur. We haven't analyzed all of them, but I want to come back and put one last picture on the board. And so I guess what I'm doing is I'm returning to our point of departure. So I want to return to the point of departure. Actually, before I do that, oops, I didn't share screen. Wait a minute, let me share screen here. Sorry, apologies, sorry. Okay, so first I want to point out that it's very, very easy to do these computations in Macaulay 2. So here's a little snippet of code that computes the Euler characteristic for a Clavial threefold. It does it pretty quickly. So it does it, you see, it takes 28 seconds to get the Euler characteristic, which is 51. And then there's an interesting thing that we do here. So this is sort of trickery. So this gives us the Euler numbers telling us the difference between H1 and H12. So we need to get our hands on either H11 or H12, and those are both more complicated computations. However, we can use local duality and sheaf duality to analyze the H11, and sometimes, essentially, if the H11, which is coming from the I mod I squared, for where I is the ideal of the Clavial, if that has a short resolution, you know for free that the H11 is equal to 1, which is the case here. So this is a very, very fast computation, 30 seconds to figure out the Hodge diamond of that particular Clavial. And so back to our last picture. So we now have gone full circle. So this is where we started. So this is the Betty table of a Clavial threefold in P8. And so the Hodge diamond is the second picture. That's not in any of the databases that we went through. So this seems to be a set of new Hodge numbers. You can't extract the Hodge numbers just from the Betty table. There's not a nice. There's examples of plenty of. Examples even in P7 of Clavials where the Betty table is the same, but the Hodge numbers are different. Of course, this is also a very coarse first measure of the Clavials that we're hunting. Nevertheless, this is an example that symmetry leads to symmetry. So I think I will now draw one last little, perhaps I stop share, and I say thanks again to our gracious host and impresario, Yang. We put, so I was going to say, and we thank our muse. And so I looked, and it turns out that the Romans had a god Janus. So there's not a counterpart in Greek mythology. So Janus is, in fact, if you Google Janus, he is the god of duality. So he's the two-faced god. So Janus is the two-faced god. He's the god of duality. So there's a good place to stop with our little, yin and yang dart, right? So the end. Thanks for your time and attention. And I pass it back to the boss. And thanks again for organizing everything.
Thank you very much, Hal. Thank you for the lovely talk. Indeed, of course, we get January from Janus, so that we have the end of the year and the beginning of another.
Exactly. That's right.
Fantastic. Does anyone have any questions? I think Andre Konstantin just raised his hand. Yeah.
Oh, I was wondering how far can you go? So to embed in P, what dimension have you tried? And if you see any pattern of those numbers?
Great question. So right now we're looking at two things. So this one for the threefolds, there's these 68 Betty tables. We haven't really started to delve deeply into them. That the example I showed was just one of them, which is easy to recognize that it lifts. So there's an issue here, which is the lifting, right? So you get these Artinian things, but not all of them lift to even irreducible Clavials. So this is the next case in P8. Of course, you might not just be interested in threefolds. If you do if you want to look at a higher dimensional Clavial, you can bump your regularity up. So if instead of threefolds in P8, if we looked at fourfolds in P7, right? So now I'm going to have a slightly bigger Betty table. There's 36 Betty tables possible there. So we haven't gone through everything, and it's because if you use the canned code to compute the Hodge numbers, it's rather slow. And what sort of saves us in making those quick computations of the Hodge numbers is that example that I had. There were 6 quadrics in 1 cubic. So we haven't delved deeply into what's out there. But I should mention, let me stick 2, I think, very interesting questions over here. So the first question is, these were Gokis inside projective space. And so if we want to use, Batirov's construction as some sort of a guideline, what about Gokis in torics? I think this is a great question, right? So, and of course, that also points out that in the situation of the torics, we have this beautiful construction of the mirror. So that's the other question, is what's the mirror, I should say. So
yeah, I guess the direction in which my question was, so it's not known whether the class of Calabi-Yau, even topologically distinct ones, is finite or not. And when you construct CCs, there are bounds. You can show that it's finite, the class. And
yeah, great question. Yeah, we haven't looked at that yet. I would guess the same. My gut instinct would be that the same thing would work for Gokis, but we haven't tried to do that yet. Good question. Thanks.
Thanks.
Right. Thank you very much. I think in the interest of time, we'll probably go